Did you know that in the past the Earth has experienced periods so cold that it became so icy that it resembled a snowball? While mankind has always had an image of a blue, hospitable Earth, it turns out that this wasn't always the case. Before plants and animals began to populate it, our planet experienced periods cold enough to see its surface completely covered in ice. How did the Earth, which lies in its star's habitable zone and on which water remains in a liquid state, turn into a ball of ice? And above all, how did it get out of this situation and become suitable for the development of life? Dear traveler, welcome. Today we're going back to the time of the super glaciations to discover these icy worlds. But before you set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Since the formation of the Earth, the atmosphere has acted as a heating blanket. In its early years, the Sun released 30% less energy than it does today. Since then, every billion years, its power has increased by 7%. Despite this, the Earth was much warmer than it is today. This phenomenon is due to its radiation balance. This is the difference between the energy received from the Sun and that reflected by the continents, oceans, and atmosphere. From the very beginning, carbon dioxide and methane have acted as a heating shield. These two powerful greenhouse gases are responsible for regulating surface temperatures. Oxygen, methane, and carbon dioxide are the main forces driving variations in the Earth's climate. In its early days, the Earth's atmosphere was mainly composed of carbon dioxide. Its concentration is gradually reduced by the erosion associated with the appearance of the first continents. Initially, this decrease was offset by the methane produced by methanogenic bacteria. Gradually, however, oxygen-producing bacteria appear. As the methanogenic bacteria die out, the concentration of methane in the Earth's atmosphere falls sharply. Climate is the result of a balance between the emission of greenhouse gases and their extraction from the atmosphere. For the Earth today, the most important natural source of carbon dioxide is volcanism. Water runoff then reacts with continental rocks to remove CO2 from the atmosphere and fix it in the form of carbonate, which accumulates as sediment on the seabed. Nevertheless, over 3 billion years ago, although volcanism was already very active, continental surfaces, and consequently erosion, were derisory, resulting in high levels of CO2 in the atmosphere. How did the very first ice age on Earth occur 2.4 billion years ago? And what are the causes and consequences for the Earth of each glaciation? Before answering these questions, let's take a look at how an ice age is defined. An ice age is defined as an episode of glaciation that took place during a past geological period. Falling average temperatures cause ice caps to expand across the planet. This phenomenon can last for millions of years. Throughout its history, the Earth has experienced at least 5 major ice ages. It is now scientifically proven that the Earth goes through cycles of climate change. The causes of these changes are diverse. Modification of the Earth's orbit, changes in solar output, geological factors. As a result, temperatures drop significantly over long periods. This is known as an ice age. During an ice age, seabed temperatures drop considerably, allowing large glaciers, comparable in size to continents, to develop over a large part of the planet's surface. The first theories on past ice ages were established in the 18th century. In 1742, Pierre Martel, an engineer and geographer, studied the scattering of gigantic boulders in random formations in the Alpine Valley. Similar patterns of boulders in other parts of the world were subsequently discovered. By the middle of the 18th century, scientists were considering the possibility of ice as a means of moving these rocky materials. It was geologist Jens Esmark who first supported the existence of a worldwide sequence of ice ages. He later proposed a theory that changes in the Earth's climate were responsible for these ice ages. In the 20th century, scientist Milutin Milankovitch advanced the concept of cycles, named after him, the Milankovitch cycles, which relate long-term climate changes to periodic changes in the Earth's orbit around the Sun. This has opened up a new approach to making predictions about future major changes the Earth may undergo. How did scientists discover that the Earth had undergone ice ages? Evidence of ice ages comes in three different forms: geological, chemical, and paleontological. Each of these provides scientists with material to develop a general understanding of the effect of ice ages over the past billions of years. Geological evidence corresponds to the stripping of rocks, the deposition of unconsolidated material, sculpted valleys. Geological evidence has its limits. They can be deformed or erased over time, and it can be difficult to date them accurately. Chemical evidence is defined by variations in the isotope ratios of fossils found in sediment and rock samples. The isotope ratio is the ratio of the number of atoms of two isotopes in the same sample. To study the most recent glacial and interglacial periods, scientists use samples of ice cores and ocean sediments. They may also contain air bubbles, enabling analysis of the composition of the atmosphere during the period under study. Finally, paleontological evidence is characterized by changes in the geographical distribution of fossils. Most organisms that live in warm conditions do not survive ice ages, whereas those adapted to colder temperatures are more likely to survive. Thus, a low fossil count in higher latitudes indicates the spread of ice caps. Scientists rely on these three types of evidence and on numerous data sources to obtain the most consistent results possible. One of the most valuable sites used as an indicator of ancient climates is the Antarctic ice cap, which has provided information on past atmospheric temperature and composition. Little Dome Sea is a drilling site set at an altitude of over 3,200 meters, or 10,500 feet, above sea level on an East Antarctic plateau. Temperatures regularly drop to minus 50 degrees Celsius or minus 58 degrees Fahrenheit. The landscape is carpeted in white, and the first coastline lies more than 1,000 kilometers or 620 miles away. Since 2021, scientists have been drilling into the ice cap to extract ice cores 4 meters or 13 feet long. The aim is to reach ice layers at a depth of 2,700 meters or 8,900 feet. The idea is to be able to go back in time 1.5 million years and reveal new information about the climate of the time. 90% of the world's ice is concentrated in Antarctica. Antarctica covers an area of 14 million square kilometers. This gigantic white continent is an invaluable archive of the Earth's history. Its ice, thousands of meters thick, contains information on its temperature and the composition of its atmosphere. Scientists are as interested in the ice itself as in the air bubbles trapped inside it. The latter reveal the concentration of various greenhouse gases, such as carbon dioxide, methane, and nitrous oxide. Drilling has enabled us to go back a long way in time. What is the origin of these climate changes? Various causes are responsible for the appearance of ice ages. Some of them are interdependent. The Earth's orbit around the Sun undergoes cyclical variations over time, known as Milankovitch cycles. During these periods, the Earth's distance from the Sun and its inclination will change, resulting in a redistribution of the sunlight received. The movement of tectonic plates influences the glaciations that the Earth undergoes. Depending on the position of the continents, the flow of warm water towards the poles can be disrupted or blocked, leading to the formation of ice caps. Variations in the amount of continental and oceanic crust affect winds and ocean currents. Atmospheric compositions such as carbon dioxide and methane concentrations is linked to ice cap movements. Greenhouse gas levels decrease with their advance and increase with their retreat. Let's take a look at the 5 major ice ages in Earth's history. $2.4 billion years ago, the Earth experienced its first ice age, which was also one of the longest in its history. This was the Huronian glaciation. This glaciation began 2.4 billion years ago and lasted until minus 2.1 billion years during the Paleo-Proterozoic era. The oceans occupy almost 25% more than their present volume, due to the degassing of the Earth's mantle. Lava from volcanic sites is rich in potassium and phosphorus, making it a high-quality fertilizer. Due to wind and weather, lava naturally breaks up and crumbles. Small pieces of material embed themselves in the fractures of the magmatic rocks and accumulate there in large numbers. As the rocks are porous, they retain not only moisture, but also a warm temperature ideal for the development of life. In the end, these seemingly inhospitable places were the scene of the development of the first organisms. Among these microbes carried by wind, weather, or tides are cyanobacteria, a type of prokaryotic bacteria with no nucleus. These unicellular organisms can live both in water and on land, in large colonies. Their metabolism is based on photosynthesis. They produce oxygen. Cyanobacteria in the air transform nitrogen into ammonium and nitrate, while those in the oceans trap carbon and produce the limestone of stromatolites. The combination of lava fragments and cyanobacterial growth gradually forms soil. Then, little by little in these same privileged environments, more complex organisms such as mosses and fungi appear. The latter will develop a method of rooting, in particular, mycenes. It was thanks in part to them that life first walked the Earth, since by breaking rocks they enabled the first terrestrial settlements. It was only later, that pollen also contributed to the proliferation of life. The Earth is not yet very conducive to the development of more complex forms of life. It is covered with active volcanoes, and toxic clouds are permanently present. Vast expanses of lava cover the ground as the sun floods in its deadly ultraviolet rays. Although cyanobacteria remain in the water, the flora is still widely dispersed. Nevertheless, a major event occurred 2.4 billion years ago that changed the face of life. It was the Great Oxidation. At that time, oxygen in the Earth's atmosphere was scarce. It remained trapped in minerals or enclosed in water. The Great Oxidation affects the Earth's waters, biosphere, and atmosphere. It can be seen as a catastrophe or an opportunity for life on Earth. Most organisms are anaerobic, but cyanobacteria are beginning to develop oxygenated photosynthesis. They occupy a new ecological niche and reproduce very rapidly by harnessing the sun's energy. Photosynthesis produces a waste product, oxygen, which cyanobacteria expel into the air. Initially, this oxygen is absorbed by the oxidation of surface iron, but as the number of cyanobacteria increases, the oxygen sinks, becomes saturated. This accumulation of oxygen in the atmosphere has had devastating consequences for anaerobic organisms, which cannot survive in the presence of oxygen. Oxygen is a highly reactive element that can disrupt the metabolic processes of anaerobic organisms by forming free radicals. These unstable molecules can damage proteins, nucleic acids, and cell membranes, leading to cell death. As a result, many of these organisms have been eliminated, leading to a mass extinction of anaerobic organisms. But increased oxygen levels have paved the way for the evolution of new life forms better adapted to these conditions. Oxygen enables much more efficient cellular respiration than other forms of energy metabolism. In other words, organisms capable of aerobic respiration can produce far more energy from a given quantity of nutrients than their anaerobic counterparts. Some organisms have evolved to use oxygen as the final electron acceptor in their electron transport chains, thereby greatly increasing the efficiency of ATP production, which could be described as the cell's energy currency. In addition, antioxidant enzymes such as superoxide, dismutase, or catalyses have evolved to neutralize toxic free radicals produced by reactions with oxygen, enabling these organisms to survive and thrive in an oxygen-rich environment. In order to survive, aerobic organisms have learned to use oxygen to breathe, eliminating the free radicals that can oxidize molecules and damage their bodies. This evolution was made possible by 3 new amino acids integrated into their genome: methionine, tryptophan, and selenocysteine. Since then, all aerobic organisms have learned to survive in the presence of oxygen, provided it remains at normal concentrations. If it exceeds these concentrations, oxygen remains unconditionally poisonous. Although this change of atmosphere was fatal to most life forms of the time, new organisms were emerging in the form of eukaryotes and metazoans. Eukaryotes include all organisms, whether unicellular or multicellular, as long as they contain a nucleus and organelles specialized for respiration. Today, eukaryotes encompass three major kingdoms of the living world: plants, fungi, and animals. The second group of organisms to develop is the metazoans. They are multicellular, consisting of a nucleus and organelles, and feed on organic matter. Their cells form tissues. The atmosphere is totally destabilized. Microorganisms have consumed most of the nutrients they needed to form oxygen. But there was another consequence for the climate. During this great oxygenation event, atmospheric oxygen increased considerably, thereby reducing methane. Oxygen combines with methane to form carbon dioxide and water. The latter do not retain heat as well as methane. At the same time, a mass extinction occurred for the majority of life forms, which were then anaerobic. For them, oxygen was toxic. At the same time, volcanic activity slowed for 250 million years. These events combined to produce less carbon dioxide in the atmosphere, resulting in a greatly reduced greenhouse effect. Temperatures fell, and the planet entered an ice age. For the first time, the Earth's surface would have been entirely covered in ice. This abrupt change in climate is linked to the transformation of the atmosphere that occurred with the evolution of life. Photosynthesis processes carried out by prokaryotic bacteria released oxygen. At the same time, the limestone that forms traps CO2, considerably reducing its quantity in the atmosphere. The reduction in greenhouse gas emissions led to a drop in the Earth's temperature. At that time, the sun provided only 85% of the energy it does today. Temperatures reached as low as -50 degrees Celsius or -58 degrees Fahrenheit for tens of thousands of years. The water present at the time becomes ice. Albedo increases, accentuating cooling and freeze-up. For millions of years, the Earth resembled an enormous ball of ice, with a surface temperature of -10 degrees Celsius or 14 degrees Fahrenheit. Scientists believe that this Huronian Ice Age brought photosynthesis to a virtual standstill. The Huronian glaciation occurred at a very early time in the Earth's history, long before the existence of dinosaurs or most of the life forms we know today. Its probable consequences have been erased by the billions of years of geological evolution that followed. The evidence of this period has been overturned by subsequent geological changes. Nevertheless, scientists have been able to trace the formation of vast glacial deposits. These accumulated in the form of sedimentary rocks, principally tillites, formed by the compaction of continental sediments containing material carried by glaciers and lamanites. Glacial activity modifies the landscape, forming lakes and valleys. Such a drop in temperature must also have altered ocean circulation and atmospheric composition. Glaciation also had a geochemical influence, modifying the cycle of elements such as iron and oxygen in the oceans. Finally, this change in climate imposed difficult survival conditions on the life forms that remained at the time, and this certainly had an impact on their evolution, as well as on future life forms. And yet, life survives the cold. In principle, below the freezing point of water, the metabolic functions of organisms are interrupted. As water crystallizes, it invades the cytoplasm in organisms. Cell tissues are destroyed, and the organism dies. Yet microbial life can persist in such a seemingly hostile environment, and the return to life following the ice ages is proof of this. When imprisoned in ice, some microbes continue to metabolize at a much lower rate than normal, depending on the temperature and quantity of food available. Others suspend all energy consumption or form spores to survive in the absence of energy. As conditions improve, mechanisms are put in place to repair cellular damage. Microbial life faced with starvation will react in different ways. Some organisms will suffer, while others will react in different ways. They may develop ultra-microcells, synthesize stress proteins, or express starvation genes to become more resistant. Another solution is to reduce metabolism and become dormant, or to form spores. Cold shock and falling temperatures also place different demands on microbes. They will develop methods to counter the loss of membrane fluidity, the reduced rate of enzymatic processes, and cell damage. Ice subjected to extremely low temperatures, such as during glaciations, displays unusual properties. Liquid veins can be found. These are insoluble impurities in the crystalline structure that concentrate in the liquid phase and form a vein-like network, measuring just a few micrometers. These famous veins contain liquid water, nutrients, and biomolecules, a veritable oasis for the metabolism of the microorganisms trapped there. However, microbes must be able to tolerate a pH as low as 0 if they are to benefit from the energy present in acidic ice veins. The acidophiles most frequently found in liquid veins are eukaryotic cells, bacteria, and archaea. There is also a surface of mineral grains dragged along by the ice, which develops a thin film of water that remains in a liquid state. This allows microorganisms to extract nutrients and the energy they need. They will have to adapt to keep their cytoplasm fluid, even when confronted with a temperature of -50 degrees Celsius or 58 degrees Fahrenheit. Despite the catastrophic situation that befell the Earth during the Ice Age, its heart continues to be active. The CO2 emitted by volcanoes accumulates under the ice and is suddenly released into the atmosphere, reinforcing the greenhouse effect and raising surface temperatures. Deglaciation then takes place in just a few tens of thousands of years. Volcanoes have also helped preserve life. They have kept certain areas out of the ice. Thanks to them, many species have been able to survive episodes of glaciation. As soon as the climate becomes milder again, species gradually colonize the regions surrounding these geothermal refuges. Studies carried out in the vicinity of these geothermal zones have shown a richness of biodiversity that diminishes with distance. Hundreds of millions of years have passed since the Huronian glaciation. The Earth has since been rebuilt. 800 million years ago, it consisted of a single vast continent, Rodinia, surrounded by a gigantic ocean, Merovia. At that time, the average temperature was 10.5 degrees Celsius, or 51 degrees Fahrenheit, and the young sun emitted 6% less light than it does today. The day lasted less than 22 hours, and the year comprised 13 months. Present-day North America forms the heart of Rodinia. Australia lies at our latitudes and Antarctica almost at the equator. As a result of magmatic movements and volcanic activity, Rodinia began to fragment around 750 million years ago. Initially, it split into two blocks, in the middle of which a new ocean, Panthalassa, the ancestor of the Pacific Ocean, was born. The part that today represents North America heads towards the ice-covered South Pole. The land in the northern half of Rodinia heads towards the North Pole. Between the two halves lies the Congo Craton. This is a hard, stable zone that was once consolidated to the lithosphere. A few million years later, these three parts will come together again to form a new supercontinent called Panatee. The collisions associated with this future meeting will give rise to mountains, the Pan-African orogeny. At this time, the mid-oceanic ripples are not very active, and average temperatures are falling. During the Varanger glaciation, the Earth actually underwent 2 glacial episodes. The first, known as the Sturtian glaciation, began 720 million years ago and ended 660 million years ago. Over the next 10 million years, temperatures rose again, forming an interglacial period. The second glacial episode, known as the Merino glaciation, occurred between 650 and 630 million years ago. These periods of severe glaciation are recognized as the most severe in Earth's history. Since the last ice age, the Earth has seen a resurgence in the diversity of life. There are new types of algae, such as chromophytes, an evolutionary grade grouping organisms with chlorophyll, but also haptophytes, a division of unicellular algae characterized by the presence of a particular extremity called a haptonym, or dinoflagellates, a class of highly diversified unicellular aquatic eukaryotic organisms. There are also hyphae, the filaments that make up mycelium and fungal spores. However, no traces of animals such as hydras or sponges have been found during this period. The parts of ancient Rodinia that reach the poles are not warm. Vast expanses of ice take shape. Soils and oceans freeze over hundreds of meters. Polar caps reach the equator. A feedback loop begins as ice reflects more of the sun's rays than darker oceans. The entire planet freezes over. Temperatures plunge to minus 50 degrees Celsius, and the thickness of ocean ice reaches over a kilometer. The Earth literally becomes a snowball. The distribution of carbon undergoes profound changes, leading to a reduction in oceanic organic productivity. Photosynthesis has halted for millions of years. Runoff water is no longer an agent of erosion. The atmosphere on Earth is distressing. The sun, although present, shines less brightly. The air is dry, cold, and unbreathable. Snowfall is rare, but powerful winds bring a little dynamism to this desolate land. No liquid water circulates. The situation seems catastrophic for life, and yet, at the bottom of the ocean, life persists in the form of algae and bacteria. And not only does it persist, but multicellular organisms also took off just after this ice age. How was this possible when everything seems so unfavorable to the concentration of nutrients and oxygen needed to sustain life? Scientists have carried out computer simulations to reproduce the snowball effect with an equivalent rate of glaciation. It appears that near the equator there are still refuge zones where the ocean would not have frozen. This is how, extremophilic organisms were able to isolate themselves in a closed environment. In the end, evolution continued and even accelerated. Microbial life could even survive and develop in solid ice. Glaciers would have played a local role in oxygenating the oceans. Certain metals, such as iron and manganese, were overrepresented in oxidized forms, testifying to a significant local supply of oxygen. The farther away from the grounding line, the rarer the oxidized forms. The grounding line is the zone between the part where the ice floats and the part where it rests on land. During this ice age, the grounding line may well have been a veritable Eden filled with oxygen. This oxygen came from small air bubbles enclosed in the compacted snow that formed the glaciers. At the grounding lines, these bubbles were released into the liquid ocean as the ice melted and rubbed against the rough bedrock. Even as the ice descends to the equator, volcanism continues, and CO2 and methane are constantly being emitted into the atmosphere. Once the concentration of carbon dioxide reaches 350 times today's level, the greenhouse effect becomes sufficient to reverse the glacial situation and melt the ice. Life can resume. Work carried out by NOAA, Planavsky, in the United States reveals that the erosion of continents during the melting of the ice released large quantities of phosphorus. Its high presence in the ocean would have contributed to the proliferation of phytoplankton and consequently the release of oxygen into the atmosphere. 1 million years, that's how long it would take for the thick mantle of ice covering the planet to melt. As a result, large volumes of calcareous deposits are formed, overlaying the deposits of the Varanger era. Over the following millions of years, the first, more complex animals appeared. The surviving cyanobacteria resumed their photosynthesis process, releasing oxygen in mass. The air changed, the microbial fauna diversified, and new life forms appeared. These are known as the Ediacara fauna. These primitive, soft-bodied animals, though still very simple compared with today's animals, are a great step forward in the world of animal life. They live mainly on the seafloor and have tough integuments that allow them to be fossilized. Most of these animals are flat. Dickinsonia holds the record, with a thickness of just 5 millimeters for a size that can reach over 1 meter or 3 feet. This facilitated tissue oxygenation without the need for organs to transport dissolved gases. Dickinsonia is a ribbed oval-shaped specimen with no mouth, anus, or digestive system. It consumes the bacterial films lining the seabed. The various organisms in the Ediacara fauna resemble jellyfish, arthropods, or leaf-like forms. Some resemble nothing known today. Most of the fossils found at this time do not fit easily into today's phyla. Cells, which until then had reproduced by dividing, were now able to stick together, thanks to a protein called collagen, to form the first multicellular animals. The latter are reduced to their simplest expression, i.e., a simple cluster of cells brought together for the benefits they all derive from it. There are no nervous, vascular, or digestive systems as yet. The sponge is the oldest animal known to have come into existence. Today, this living fossil numbers some 10,000 species. The sponge's body is soft and pierced by numerous tiny holes called pores. It is through these pores that the water passes and is filtered to extract the nutrients the sponge needs. The body is supported by a skeleton composed of limestone or silicon. Sponges have an extraordinary capacity for regeneration. Once a part has been removed, it grows back without being damaged. Sponges have a very wide distribution, having colonized both fresh and brackish marine waters to depths of over 5,000 meters or 16,400 feet, as well as shallow waters, regardless of climate. After a period of calm, the climate became capricious again, and a new glaciation occurred during the Upper Ordovician and Silurian periods, around 460 to 420 million years ago. During the Ordovician period, which began 485 million years ago, the continents were grouped together to form the supercontinent Gondwana. This was formed by the fracturing of Rodinia. The history of our planet is punctuated by the merging and separation of its land masses under the effect of plate tectonics, and the continents never stop moving. While Gondwana settles at the South Pole, 3 other smaller continents, Laurentia, Siberia, and Baltica, and their islands head north to find a warm home near the equator. Here they experience the vagaries of a tropical climate, a hot sun and violent rainfall. The rain that falls from the sky carries with it carbon dioxide from the atmosphere. Combined with the heat, the rocks are dissolved. Carbon-containing ions are released and carried by runoff into the oceans. Marine animals use them to build their shells and skeletons. When they die, the carbonate material is stored in sediments on the seabed. In the long term, the process of taking carbon from the atmosphere and burying it on the ocean floor considerably reduces the amount of atmospheric CO2. The CO2 released by erupting volcanoes is not enough to compensate for these losses. The greenhouse effect diminishes, and temperatures on Earth begin to fall too. This ice age is not, however, an icy one. We're not talking about a snowball Earth here. It's even likely that in its early stages, it contributed to the development of biodiversity. During this period, the number of marine animal genera increased, known as the Great Ordovician Biodiversification Event, or GOBE. The rapid diversification of plankton favors the development of fauna living on the ocean floor. Cambrian trilobites, inarticulate brachiopods, and eucrinoids gave way to cephalopods, crinoids, and articulate brachiopods. Continental seas are shallow and rich in life, and the first coral reefs appear. Mollusks become common, especially bivalves, gastropods, and nautiloids. Corals appear, colonizing the oceans and building immense reefs like veritable ecosystems. They helped enrich the marine fauna. By the end of the Ordovician period, the oceans were teeming with species, each more diverse and varied than the last. From starfish and sponges to sea scorpions and other extraordinary species of clumsily swimming primitive fish. It was also at this time that the first large predators appeared. Until then, animals had been almost exclusively benthic, staying close to the seabed, but orthocerid cephalopods were the first to swim in open water. Trilobites had better watch out, because the terror of the seas is approaching. Here we see a Camaraceras. Sporting a straight cone several meters long, it has tentacles that it can wave from all sides. Its bulging eyes enable it to spot its prey in search of its next meal. With a single stroke of the beak, the carapace of a trilobite breaks in two. From now on, the entire food web becomes more complex. Biodiversity may appreciate the drop in temperature compared with the Cambrian, but it will have trouble coping with the next challenge. The Andes-Saharan glaciation contributed to one of the 5 greatest mass extinctions in Earth's history, known as the Ordovician-Silurian extinction. Following this extinction, 70% of species disappeared from the Earth's surface. But what was the origin of this glaciation? Far away, several thousand light-years from Earth, a star exploded in a supernova. The gigantic burst of energy releases gamma rays that reach the Earth at the speed of light. These rays penetrate the atmosphere, altering the ozone layer and darkening the planet. Nitrogen and oxygen are transformed into the toxic gas nitrogen dioxide. The latter engulfs the planet to the point of blocking the passage of sunlight. This theory has little support in the scientific community, as the main obstacle to its acceptance is the difficulty of proving it, as traces of the supernova have long since disappeared. But another cause could have had an impact on the climate of the time. Although solar luminosity was around 4.5% less intense than today during the late Ordovician period, a decrease which under today's climatic conditions would lead to glaciation, the atmospheric concentration of carbon dioxide was considerably higher, reaching levels up to 18 times higher than today. This high CO2 concentration would normally have exerted a powerful greenhouse effect, counterbalancing the lower solar luminosity. Parallel to these factors, the Appalachian orogeny was underway, a geological process that spanned approximately 325 to 260 million years. This phenomenon was the result of the subduction of the oceanic tectonic plate beneath the North American continental plate. This geological process contributed to a massive reduction in atmospheric carbon dioxide levels. The explanation lies in the silicate weathering mechanism, a chemical reaction accelerated by the newly formed mountains, which captures carbon dioxide from the atmosphere and stores it in the Earth's crust. In addition, tectonic plate movements have led to significant changes in the distribution of continents, which may have influenced ocean and atmospheric currents, thus modifying the climate. To this we can add the Earth's orbital variations, which also have the potential to influence climate by altering the incidence of solar radiation on the Earth's surface. Whatever the cause, glaciation is underway. As ice accumulates on the continent, sea levels drop. Shallow marine areas are reduced. The first links in the food chain are affected, resulting in famine for all organisms. What was once an ocean teeming with life is totally devastated. In just over 500 years, a third of the existing fauna had disappeared. Another 100,000 years later, the famine continues. Glaciers sucked water from the ocean. Shoals are drained, drying up. The sea retreats several hundred meters, but once again life will prevail. Beyond a certain depth, organisms can find refuge. Nautiloids and eurypterids seek shelter on the seabed. Other animals adapt to cold water. Such is the case of the astrapus. This small primitive fish of the ostracoderm family, barely larger than a hand, has no fins and moves with the back of its body. To feed, it sucks up small invertebrates living on the seabed or the debris of dead animals. Its skin is highly sensitive to vibrations, enabling it to escape the predators of the time. Astrapus was the first to feature a primitive backbone. This creature, relatively insignificant at first glance, is in fact the first known vertebrate fish. This lineage would later give rise to birds, reptiles, and mammals. Astrapus proved particularly resistant to this new ice age. It follows the retreating ocean. It is a picky eater, feeding on whatever it can find. It also tolerates cold water better than other aquatic creatures. The Astrapus adapts to this new ordeal, and soon a new variety of fish is born. These were equipped with the first gills, enabling them to absorb food more easily. It would be another 500,000 years before the planet began to warm up. At last, the glaciers melted. But for the species that had managed to survive the Ice Age, it was a new climatic upheaval. The toll was heavy. Over 70% of species disappeared forever. Thanks to nature's formidable resilience, life will resume and write a new chapter in the history of the Earth. The oceans will be repopulated by astonishing species, and the planet will gradually return to its tropical climate until the next ice age, which began in the Carboniferous period around 320 million years ago. We're in the Devonian over 400 million years ago. This was a pivotal period for vertebrates, but also for vegetation. The Earth is still mostly covered by the immense Panthalassa Ocean. Proto-Gondwana slowly slides northwards. It is set to collide with the young continent of Laurasia, formed a few million years earlier. These two continental blocks would unite at the start of the next period, the Carboniferous, to form a single continent, Pangaea. At this time, the ice caps were absent, and the Earth enjoyed a relatively mild climate, around 25 degrees Celsius, or 77 degrees Fahrenheit. The weather was warm and vegetation thrived and conquered terra firma. The first terrestrial plants, characterized by lichens and mosses, appeared around 500 million years ago. Over millions of years, creeping plants evolved into ferns and lycopods, until during the Carboniferous period, over 350 million years ago, for the first time in Earth's history, they became rich in abundant vegetation. Thanks to warm, humid temperatures, the first insects proliferated. For the time being, they are the only terrestrial inhabitants. There are currently no herbivores. As a result, plants are literally colonizing the Earth. The first forests formed, vegetation diversified and became abundant. Large tree ferns grow alongside lycopods a few meters high. The first broad-leaved plants appear. Thanks to photosynthesis and the resulting oxygen, the Earth's atmosphere is enriched with oxygen, which will not be without consequences. Indeed, the rise in oxygen levels combined with high atmospheric pressure favored the most energy-intensive metabolisms, and large terrestrial vertebrates grew to titanic proportions. One of the best-known examples is the dragonfly, Meganeura, with a wingspan of up to 75 centimeters or 30 inches. There's also the Arthropleura, a distant ancestor of millipedes, which measured up to 1.8 meters or 6 feet in length. Rising oxygen levels also led vegetation to become more resistant to fire. It was also at this time that flowering plants appeared. Increased plant development leads to the absorption of large quantities of atmospheric CO2, which considerably reduces the greenhouse effect. Lignin and cellulose from tree trunks and plant debris accumulate. A polar climate process is triggered. Summers are now too cold for winter snow to melt. the snow accumulates and creates sufficient pressure to form ice. Albedo rises as the ice sheet, an ice sheet covering the mainland, expands. A feedback loop is triggered, and the ice extends further and further. Under the effect of this climate change, plants are forced to slow down their evolution. The high oxygen level triggers fires despite the prevailing humidity. The combination of slower vegetation growth and the occurrence of fires causes a further increase in carbon dioxide in the atmosphere, preventing a snowball effect through greenhouse warming. Over the years, the drop in albedo leads to warmer summers and milder winters, limiting snow depth in areas where glaciers grow. The melting of ice caused by global warming leads to a rise in sea level, which now covers the anoxic zones that used to trap carbon. The Earth now has less surface area to sequester carbon, and a greater proportion of carbon dioxide returns to the atmosphere. The Karoo glaciation came to an end 260 million years ago, bringing the Earth's atmospheric oxygen levels close to those of today. Since then, there has been no ice age until the one we're currently in, the Pliocene-Quaternary, which began around 2.58 million years ago. At the end of the Pliocene, today, we are in the last Great Ice Age. It began during the Upper Pliocene some 2.58 million years ago. We are currently experiencing an interglacial period, which is reflected in the retreat of glaciers accompanied by global warming. The current Ice Age is known as the Pliocene-Quaternary Glaciation. Since its beginnings, the Earth has undergone several glacial and interglacial periods. Ice caps advance and retreat on timescales ranging from 40,000 to 100,000 years. In the past, they covered the entire globe. Today, they are limited to Greenland, Antarctica, and a few smaller glaciers, such as the one covering Baffin Island. 2.58 million years ago, the continents were roughly as they are today. Scientists estimate that they have not moved more than 100 kilometers, or 62 miles, in relation to each other since the beginning of this period. During the previous period, the main change was the connection between North and South America. As a result, the Isthmus of Panama is formed, causing the disappearance of warm equatorial currents and the onset of an Atlantic cooling cycle. The climate gradually became drier and colder. The Greenland ice sheet appears, while the Antarctic ice sheet thickens. The collision between the African plate and Europe continues. The Alps continue to orogenize. Combined with tectonic movement, erosion phenomena, and the trapping of atmospheric CO2 in the form of carbonates continue, reducing the concentration of CO2 in the atmosphere. These phenomena are leading to global climate change. Tropical forests are shrinking, with only a small portion remaining around the equator. Savannas and grasses are now conquering every continent. Temperate forests of deciduous trees are found at mid-latitudes, and conifers and tundra at high latitudes. Antarctica is a veritable frozen desert. The marine and terrestrial faunas, although primitive, are now modern. The junction of North and South America and the formation of the Isthmus of Panama have brought about a great deal of inter-American exchange. A wide variety of animals can now migrate from south to north and from north to south. Mammals, reptiles, amphibians, arthropods, and even flightless birds. Mammals, represented by rodents, mastodons, and opossums, are widespread in North America. We also find Gomphotherium, a now extinct species closely resembling today's elephants. It has 4 almost upright tusks and a short, tapir-like proboscis that falls back on the lower jaw. Sloths, glyptodons, and armadillos migrate northwards across the Isthmus of Panama. Carnivores diversify. They include dogs, bears, and canids. In Eurasia, while the presence of primates diminishes, rodents are widespread. Giant rodent species roam the planet's surface. A giant rodent fossil, Joseph-Fortigacea monesi, was discovered on a beach in Uruguay in 1987. It appears to be the largest and heaviest rodent known today. Its closest relative today is the pacarana, a rodent that weighs between 10 and 15 kilograms, or 20 and 35 pounds, and lives in the tropical rainforests of the Andes. Joseph-Fortigacea monesi, on the other hand, measures up to 3 meters or 10 feet in length and weighs up to a ton. His skull alone measures 57 centimeters or 23 inches. In comparison, it's as tall as a bison. Its morphology is similar to that of a guinea pig, but proportionally the size of a hippopotamus. Its jaw is exceptionally strong. In Africa, primates continue to evolve, and ungulates dominate. It was also at this time that the first humans and giraffes appeared. The number of bovid species increases. For the first time since the Cretaceous, and thanks to the great Inter-American exchange, North American species mix with those of the South. Marsupials remain dominant in Australia. Wombats and kangaroos appear. Platypuses appear. As the climate changes, tropical flora is replaced by subtropical forests and grasslands. Western Europe was enriched with trees from the birch, oak, and ash families, as well as conifers further north. But the Earth is affected by a gradual cooling, and vertebrates are not indifferent. Evolution continues, but it's getting poorer. Perissodactyl ungulates decline. Conversely, the large artiodactyl ungulates fared much better, as they were satisfied with a coarse diet and better able to withstand periods of food shortage. Mastodons, these gigantic herbivorous mammals, proliferated, and the first elephants appeared. All these giants were an important source of food, and new larger carnivorous mammals appeared. Most of the fauna that reigned at the end of the Pliocene no longer exists today. The ice ages of the next few thousand years took their toll on many of these animals. Some were able to migrate to milder latitudes, while others were doomed to extinction. Even if winters were no harsher than today, the difference lay in the fact that summer no longer existed. The exact number of glaciations during this period is open to debate. 4 major glaciations have been clearly identified, separated by interglacial periods. These were the Gunns Glaciation from 760,000 to 530,000 years ago, the Mindell Glaciation from 650,000 to 350,000 years ago, the Risk Glaciation from 300,000 to 120,000 years ago, and the Worm Glaciation from 80,000 to 10,000 years ago. An important detail in the history of the Earth differentiates this ice age from the others. Man is now at the heart of the glaciations. In fact, it was thanks to these ice ages that the great human adventure began. climate change means lower sea levels. Far from being a tragedy for mankind, this is actually a door opening for our ancestors from the African continent, Homo erectus, to travel north. In Europe, the cold sets in a little more each winter. Forests wither for lack of water. Oak forests give way to cold, arid steppes. The herds of animals that still roam the plains in search of moss and lichen are a godsend for the human tribes living in Europe. With their rudimentary tools, they catch the young animals and take the adult ones that have already died. As the years go by, the extreme cold sets in, with temperatures dropping to minus 30 degrees Celsius or minus 22 degrees Fahrenheit. Glaciers extend as far as Scotland and the northern Netherlands. The tribes of men, who may have ventured out before, return down in search of warmer lands and temperatures. At this time, fire still eluded them. Ice caps more than 3,000 meters or 10,000 feet thick cover Greenland, North America, and Siberia. All the water used to form these glaciers has caused sea levels to drop by 100 meters. New lands are revealed. The men who populate the African continent now have new prospects. Europe and its herds of reindeer were all the more attractive as the tropical forests had not withstood the heat, and savanna and desert now decorated the landscape. This glaciation lasted for around 80,000 years until an interglacial era began, with the climate warming for around 20,000 years. This cycle has been repeated 4 times to date. It has to be said that the most common state of our planet over the last few million years has been glaciation. In the midst of these glaciations, man has been able to adapt. He protected himself against the cold. Glaciations opened up passages in the sea, and man has continued to travel through glaciations and deglaciations. The event that forever changed its relationship with the climate was the domestication of fire 400,000 years ago. From then on, it penetrated cold regions. They could now set up camp, build shelters and cabins. They can live on permanently frozen ground, their means of heating eternally at hand. After an ice age lasting over 90,000 years, the last great deglaciation began 21,500 years ago and lasted around 10,000 years. At the end of this period, the Earth underwent profound changes. Its average temperature rose by around 4 degrees. The gigantic ice caps that once covered a large part of the North, as far north as Belgium in Europe, melted. Sea levels rose by more than 100 meters. Flora was radically transformed, and the global water cycle intensified. Over 20,000 years ago, the Earth's climate was stable. Atmospheric CO2 levels were relatively low. It was cold, and the oceans were much lower than they are today. 19,000 years ago, a tiny area in the north began to warm up, while the south remained cold and hardly changed at all. CO2 is still low, and the ice caps are not moving. This evolution of the north is undoubtedly due to orbital changes that brought the Earth closer to the sun in summer, while the south was plunged into shadow. The continents are concentrated in the north at high latitudes. This is where the ice caps were formed. Even the slightest warming, of the order of a fraction of a degree, is enough to cause a large volume of ice to melt. Fresh water then flows into the Atlantic. The Atlantic is like an ocean corridor, linking the 2 poles. It carries warm water from the intertropical Atlantic far northwards. Once in the polar zone, this water loses its heat to the atmosphere. It becomes denser and sinks to the depths before flowing southwards. This circulation brings heat from the southern hemisphere to the northern hemisphere. However, if an influx of lighter fresh water occurs in the North Atlantic, the heat in the south may have accumulated as the north cooled. This phenomenon may explain why, 17,500 years ago, the situation shifted. Temperatures in the south rose and the north cooled. Atmospheric CO2 levels rise slowly. After 1,500 years, temperatures in the north also start to rise again, along with the amount of atmospheric CO2. This time, 16,000 years ago, warming affected all latitudes and zones. Atmospheric CO2 levels rose at a faster rate. According to scientific research, warming in the southern hemisphere caused massive degassing of the Southern Ocean, releasing massive amounts of carbon dioxide. By 10,000 years ago, warming had reached its definitive value. Atmospheric carbon dioxide levels stabilized. Over the next 4,000 years, the ice caps will retreat. This scenario could foreshadow the future of our planet if it is subjected to another episode of massive warming. In just 3 centuries, human activity has produced and released into the atmosphere 30% more carbon dioxide than during the last deglaciation, which lasted 10,000 years. For just over 10,000 years, the Earth has been in an interglacial period, characterized as a warm period known as the Holocene. Melting glaciers caused sea levels to rise to their present levels 6,000 years ago. It was at this time that the Black Sea began to fill up. The ice sheets gradually melted, and the land that had been hidden beneath them was freed from the ice and brought to the surface. Temperate fauna and flora reclaimed the middle and high latitudes. As for those that were adapted to the cold climate, they occupy other ecological niches. The rise in temperature during this interglacial period is not without consequences. In tropical zones, rainfall increases, leading to the shrinking of deserts. Rising sea levels isolate the British Isles from the European continent, moving habitable areas northwards. While flora and fauna have not changed significantly, the distribution of species has. Herds of large herbivores left the tropics as they became invaded by vast expanses of forest. They are now interested in the savannas that have appeared in the northern and southern deserts. In the northern hemisphere and Australia, megafauna are becoming less and less present. Large mammals are affected by a wave of extinction. The disappearance of mammoths and other large herbivores has had an impact on the climate. When these animals were present 12,000 years ago, they emitted 9.6 million tons of methane per year. As they disappeared, atmospheric methane levels fell, and so did the greenhouse effect, causing the planet to cool. The mammoth was a remarkable animal. Closely resembling today's elephants, it had a large head with a trunk, and a massive body with 4 pillared limbs. The largest species reached between 6 and 8 tons. Throughout their evolution, they adapted to ice ages and cold waves. The size of their ears and tails has diminished considerably. The hair, most exposed to thermal shock, could reach a meter in length. Their wool was 6 times thicker than a human hair. Their highly developed sinuses enabled them to process immense quantities of cold air. Their prominent tusks could reach up to 5 meters or 16 feet, an ideal tool for flushing out grass buried under the snow. Mammoths aren't the only ones affected by the extinction wave. In Australia, large species of reptiles and marsupials are disappearing. In North America, megafauna are not spared either. Mastodons, relatives of mammoths and elephants, are suddenly disappearing. The great land sloths, which grew to the size of cows, did not survive. In the family of large carnivores, the American cheetah, the saber-toothed tiger, and the American lion are no more. Giant armadillos, giant bears, and giant beavers have also disappeared. Man's favorite game, the herbivorous wood-eating mammals such as the antelope, are also disappearing from North America. This megafauna has a long lifespan, a low mortality rate, and a slow population increase. Few predators are capable of attacking their adult specimens. Nevertheless, megafauna are highly vulnerable to climate change. The arrival and spread of early man coincided with the beginning of the extinction wave. The mammoth is an animal that provides mankind with everything it needs: ivory for tools, bones for building huts, fur for covering up and protecting itself from the cold, meat as food, and even grease to keep the fire burning. Man has therefore not hesitated to overhunt this giant of history, contributing to its disappearance. But man and hunting were not the only factors behind the mammoth's disappearance. Mammoths were extremely well adapted to the cold. Global warming during the Holocene caused the evolution of grass and shrub-filled steppes into coniferous forests and tundra regions. Although herbivorous, the mammoth's dentition was probably not equipped to consume tree foliage. Some species, such as the woolly mammoth with its thick fur that kept it warm even in freezing climates, could have died out from hypothermia, while others, such as the bison, have adapted to climate change. The increase in temperature on Earth has not been sustainable for them. Ever since the discovery of the ice ages in the 18th century, mankind has been wondering whether an ice age might return. The Earth is currently in an interglacial period. The periodic and alternating nature of glacial and interglacial periods is now well established, as is the inevitable return of the ice ages. Since its very beginnings, the Earth's climate has been influenced by greenhouse gases and astronomical forcing. The latter is due to the slow changes in the inclination of the Earth's axis and the shape of its orbit. Glaciations in the Northern Hemisphere during the Quaternary era are punctuated by variations in obliquity. The first ice ages, between 3 and 1 million years ago, occurred in regular cycles every 41,000 years. Over the last million years, the periodicity has increased to 100,000 years. The ice caps go from deglaciation to glaciation when astronomical forcing crosses a critical threshold, and vice versa. 420,000 years ago, the interglacial period lasted almost 30,000 years instead of the usual 10,000, because astronomical variations were not strong enough to reverse the system. The Earth is still in this situation today, and it is possible that the interglacial period we are currently in will persist naturally for another 50,000 years if the carbon cycle remains undisturbed. The study of the carbon cycle on the scale of the last century has enabled us to better understand how it works. One of the theories put forward is the hypothesis of a return to the initial natural state thanks to the erosion of silicate rocks, which make up a large part of the Earth's crust. Erosion increases in hot, humid climates. Erosion consumes CO2, transforming it into basic carbon. As a result, ocean acidity decreases. This is a natural factor that has certainly kept liquid water on the Earth's surface for over 4 billion years. This theoretical approach does not take into account the influence of the organic carbon cycle. A significant proportion of this element is buried in organic form, making its dynamics much more complicated. A possible return of the ice ages is therefore not immediately foreseeable. In 50,000 years at the earliest. Do you think that by then mankind will have found ways to adapt to a new ice age?